Today, I'm going to discuss spectral lines. In short, these are the specific wavelengths of light that an element or molecule will emit as a gas. To explain this, I first need to discuss energy levels in atoms. The most accurate model of the atom states that the protons and neutrons are confined to the nucleus, with the electrons surrounding it in a cloud of probability. While we may not be able to identify the exact location of the electron, we do know it is confined to certain energy levels. At this point, it is important to note that, like everything, electrons are both a particle and a wave. So, for this explanation to make sense, we need to interpret electrons as a wave. Now, in an atom, the electron wave circles the nucleus, and, for the electron to exist, the two ends of the wave have to meet up. If the two ends of the wave do not meet up, the wave will interfere with itself, canceling the electron out to nothing. There are two ways to get the electron wave to meet up with itself. Either change the wavelength of the electron, or change the radius at which it surrounds the nucleus. For all intents and purposes, the wavelength of an electron is constant, so our only option is to change the average radius of the electron wave. We cannot use just any radius. Only some distances from the nucleus will work. If the electron is not at one of these distances, the wave will not meet up with itself, which leads to interference, which cancels the wave out. Since electrons and protons interact via the electric force, each of these distances has a different energy. This is where the discrete energy levels come from. If an electron is not at one of these energy levels, the electron cannot exist. Since there are multiple distances from the nucleus where the electron wave can meet up with itself, there are multiple energy levels for any atom. The farther from the atom, the higher the energy each level will have, and the closer the spacing between individual levels. For example, if the first energy level in an atom is defined to have 0 energy, the second level might have 10 electron volts, while the third has 12 electron volts, electron volts being a measure of energy. This is a 10 electron volt difference between the atom's first two levels, but only 2 electron volts between the second and third energy levels. This pattern of higher energy at smaller spacing continues throughout the atom. Due to the decreasing spacing, there is a maximum energy for the energy levels. Above this energy, the electron is no longer bound to the atom. It is a free electron. However, we do not care about that situation here. The values and spacing of each energy level varies for different elements and molecules. However, the energy levels are identical between atoms of the same element or molecule. It is important to note that electrons want to be at the lowest energy possible, so they will try to be at the lowest energy level possible. However, based on the Pauli exclusion principle, only a certain amount of electrons can occupy a given energy level. As such, electrons not fitting into the lowest energy level will go to the next lowest one, and so on until all electrons are in their lowest possible energy levels. When an atom is in this lowest energy condition, the atom is said to be in its ground state. While electrons want to be in the lowest energy level, they can be excited to higher energy levels. When an electron gets some energy, it will jump to a higher energy level, corresponding to the amount of energy it received. An electron can gain energy by being jostled by thermal energy, absorbing a photon, or a multitude of other ways. When all the electrons are not at their lowest possible energy level, the atom is said to be in its excited state. Atoms do not like to be in their excited state, so pretty soon after being excited, the electron will fall back down to its ground state energy level. However, the electron does not need to fall directly to its ground state. It could stop at other energy levels along the way. So, if an electron is excited to the third energy level, it could either fall directly to the first energy level, or it could fall to the second energy level and then to the first. This drop releases energy in the form of a photon, or multiple photons if multiple drops occur. There is a direct relationship between energy and wavelength for light, so the energy of the photon will determine the photon's color. As explained earlier, energy levels have discrete values, so the difference between any two energy levels also has a discrete value. This means that a given element will only produce certain discrete colors of light, called spectral lines. The light produced need not be in the visible spectrum. In fact, many of the discrete colors are ultraviolet, with some energy level drops creating infrared. In either case, a gas will only produce a certain set of spectral lines, called an emission spectrum, rather than the full continuous spectrum. Now, just as electrons only emit photons of certain energies, so too can they only absorb photons of certain energies. Since electrons cannot exist between energy levels, and photons cannot transfer only part of their energy, electrons will only accept certain photons. These photons have to excite the electrons exactly to a higher energy level. This discrete acceptance of photons leads to the absorption spectrum, which is an otherwise continuous spectrum of light with a few dark bands. Since the difference between energy levels is the same, whether an electron is being excited or falling, the dark bands in the absorption spectrum correspond to the bright bands in the emission spectrum. It is worth noting that discrete spectral lines are only created by gases. This phenomenon does not occur in higher density materials, like solids or liquids. In these higher density materials, the atoms interact with each other, changing the energy levels in each atom. When atoms get close enough to each other, as they do in solids or liquids, the energy levels of each of the atoms combine to form a continuous energy band. As such, there are an infinite number of possible energy levels, meaning there are an infinite number of differences between energy levels. So, an electron that falls from an excited state back to the ground state in a solid or liquid can emit light of any energy, and thus any color. So, high-density objects emit the full spectrum of light, rather than a few discrete wavelengths. As I mentioned earlier, each gaseous element and molecule has its own unique energy levels. This means that each element and molecule emits a unique set of spectral lines. Furthermore, the energy levels between atoms of the same element or molecule are identical. This means that all atoms of a given element or molecule will produce the same set of spectral lines. So, one way to identify an atom or molecule is to look at its emission spectrum. This is especially useful when you want to analyze the chemical makeup of something from a distance, as you only have to look at the light it produces. For this reason, analyzing spectral lines is often used in astronomy, to identify the composition of stars, galaxies, and other distant objects. It is from these emission spectra that we know the Sun is made up mostly of hydrogen, with a chunk of helium and trace amounts of other elements. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.